Good morning, students. Teacher Betty, again taking you through advanced inorganic topics. Lesson 2. In lesson 1, we looked at a few points and we said that boranes, boron does not combine directly with the hydrogen to form hydride. And we said the instability of the hydride formed in case boron combines directly with the hydrogen is due to the presence of the empty pz orbital. We went further to say that, however, it can form a variety of stable covalent hydride. An example was the diborane 6, and the stability was attributed to the formation of the bonding electron, distribution of the bonding electrons among all the valence atomic orbitals, resulting into the formation of the molecular orbital. We looked at the nomenclature or the naming of the boranes, and we said the number of boron atoms are named by the Greek numerical prefixes, where we said if they are 4, they can be tetra, 5, penta, 6, hexa, and so on. While the number of hydrogen atoms in the boron molecule is named by Arabic numerals, indicated by 1, by 6, 9, 10, as the case may be. An example, if there are 4 boron atoms in boron molecule and 10 hydrogen atoms, that boron is named as tetraborane 10. If there are 5 boron and 11 hydrogen, then that one is pentaborane 11, and so on and so forth. So today, let us look at the preparation of diborane. We can use the Stokes method, whereby when magnesium boron is treated with the aqueous solution of hydrogen chloride or hydrochloric acid, it results into a mixture of various boranes. These mixtures contain mainly the tetraborane 10, and on heating of the tetraborane 10 results into the formation of the diborane. An illustrative equation is shown. Manganese boron plus the acid results into the tetraborane 10. On heating of tetraborane 10, diborane is formed. Another method is by passing an electric discharge through a mixture of boron chloride or boron bromide and excess hydrogen. Boron X, where X is either chlorine or a bromine, plus hydrogen and an electric discharge, it results into a diborane. Another method is the action of boron chloride. When the ionic hydride, like a sodium hydride, calcium hydride, is treated with the boron chloride, it results into the formation of the diborane. An illustrative example or an equation is given below, resulting into the formation of the diborane. Even though we use calcium hydride, it results into the formation of the diborane. Another method is by the reaction of the complex hydride on hydrogen chloride or on iodine and others. So when we react the complex hydride, lithium hydride, with the hydrogen chloride under 180 degrees negative Celsius, results into the formation of the diborane. Sodium hydride plus the iodine, again, we get the diborane, and so on and so forth. Let us look at the properties of the diborane. Diborane is a colorless gas, has a sweet odor, extremely reactive gas and toxic, with a melting point of -165 degrees Celsius and a boiling point of -925 degrees Celsius. Action with heat. Diborane is stable at low temperatures and in absence of moisture. However, at high temperatures, it gives higher boranes, like the pentaborane 10, the pentaborane 11, tetraborane 10, octaborane 9, and so many others. At red heat, diborane gets decomposed into its constituents, into boron and hydrogen. And action of water and aqueous alkali, the diborane produces hydrogen. When we react with water, it produces hydrogen. Also, an action of an alkali, it will produce hydrogen. Action with the air or oxygen. Pure diborane undergoes no reaction when mixed with the dry air or oxygen at room temperature. But when it is impure, it produces water and other product, and the reaction is exothermic, resulting into the production of 2,165 kilojoules of heat. When we react with an electric discharge, action with an electric discharge, in the presence of an inert gas, diborane decomposes into a mixture of boranes, the tetraborane 10, about 40%, pentaborane 9, about 20%, and the pentaborane 11, about 30%, and small quantities of other products. These components can be separated by fractional distillation. Formation of metallic borohydride. When diborane reacts with ionic hydride, it results into the formation of other products. Borohydrides of the metal is obtained. For example, diborane plus the metal hydride, we get the borohydride of the metal. So is the lithium borohydride, and aluminum borohydride can also be obtained. Action with halogen. Diborane react with the chlorine at 25 degrees Celsius to form hydrogen chloride, and the bromine react at 100 degrees Celsius to produce hydrogen bromide. The illustrative equations are given below. With the chlorine, we get the hydrogen chloride. Then with the bromine, we get the hydrogen bromide. An assignment I can leave you with: look at how the diborane reacts with ammonia. Also look at the methylation of the diborane, formation of additional compounds. Consider sodium and potassium. You can also look at the action of alkanes and alkynes, the process known as hydrobolation. Uses of the diborane. is used as a rocket fuel for the preparation of high energy fuel and propellants. It can also be used for the preparation of higher boranes, organic boron compounds, and metallic borohydride, like lithium borohydride, sodium borohydride, aluminum borohydride, and others. It can be used as a reducing agent in organic chemistry and as a catalyst in the polymerization reaction. And lastly, can be used in the welding of torches. Next time, we are going to look at the structure and bonding in diborane molecule.